All right, hello everyone. Hopefully you had a good break and you've had some good time to revise the organic properties section of the course and do the practice questions there. So we're going to keep going on today looking at organic reactions, which will finish off chapter 11. So fortunately, we've actually talked about a lot of these reactions before. So hopefully about half of them you've seen before. We'll go over those ones again if you don't remember them, and we'll cover some new ones as well, and then talk about a little bit of the maths we can do in terms of organic reactions to describe them. So just looking at the learning intentions from the curriculum. So there's a whole dot point on organic reactions, and we've got a few different ones here. So note that you do need to be able to write an equation, and you need to know the specific reagents for each reaction. So we've got oxidation of primary and secondary alcohols, substitution reactions, addition reactions, hydrolysis reactions, condensation reactions, and esterification reactions. So there's 6 there. We've already talked about substitution, addition, hydrolysis, and esterification. So we've already talked about 4 of those. Hopefully this will be more of a refresher rather than a lot of new information. And then you're going to need to know about pathways as well. Pathways is more of an application of the organic reactions, using multiple of them in a row, basically using them kind of like a flow chart to get from point A to point B. So I've split that up here. So you should be able to predict the product produced or the reagents needed for a specific organic reaction. You should be able to describe a sequence of organic reactions. So let's write a pathway to turn a specific reactant into a specific product. And you should be able to calculate atom economy and percentage yield for a given reaction, given the appropriate numbers. All right. So what we're going to do is that we're going to make a flowchart of all of the different reactions here. So you can kind of grab mine off the PowerPoint if you'd like. I'd highly recommend writing one down somewhere, just so you have like one as an A4 sheet. You don't get any of these reactions given to you in the data book, so it is up to you to remember them and remember the reagents and things like that. So there is a bit more of the memorization in this chapter than maybe you used to from the other chapters of chemistry, where a lot of it is kind of application based. You do need to know a few reagents and things like that. So we're going to do everything here based on a specific compound. Now I've just chosen ethane, and we'll have ethene as the starting compounds basically, and we'll talk about different things we can make from those. Now I could theoretically have made this so that this was R, so it just worked with any organic group. Doesn't really matter. If you had a bigger compound, for example, you had butane or something, you could imagine that it was just a bit longer. We're mostly going to be talking about reactions that just happen at the end here. Of course, the same reactions would work on this end or here, unless I've otherwise stated. All right, so the first one to talk about is we've got substitution. So as the name suggests, this is where we're going to swap 2 atoms around. This is most important for alkanes. So starting off in this top left, we've got an alkane. The only thing we're really going to be able to do to that is substitute it. Technically, a reaction that all organic compounds can do, or at least most, is combustion, but that's not particularly useful from a synthetic perspective, and we've already done combustion reactions to death. So yes, you can imagine that every single compound that we've got can point up to the carbon dioxide molecule up here if you'd like, but it doesn't really take a whole lot of nuance to make carbon dioxide, and there's plenty of carbon dioxide just around in the air and stuff and coming out of factories. So it's not really a high priority synthetic target. So the main reaction we want alkanes to do is substitution. We already mentioned that. So substitution, we're going to react an alkane with a halogen. I've chosen chlorine here just to have something consistent. If you want, you could write X just to represent a generic halogen, or you could replace that with anything. You could replace the chlorine here with F, fluorine, and just have all of the chlorines be fluorines and do basically the same reaction. Be slightly different just because of the size and the electronegativity of the different atoms, but for the purposes here, we'd say the same reaction would end up played out. Note that our reagent here is that we need the halogen, and we're going to need UV light. You need to say UV light there if you're writing a reaction there. It won't actually occur without UV light because it's quite a difficult reaction to get kick-started. Most other reactions will work without it. You can just kind of heat it up. You can't just heat this up to work. You need UV radiation. And hopefully you remember from before that we're going to end up with different degrees of substitution. A lot of the time you'll see something like a single substitution, which just means the first one here. So yes, the product from the first one can go and react again and react again and react again. So you'll probably end up with a mixture if you do this reaction somewhere. But so if you are asked to write a specific reaction out, it'll probably say something like single substitution. So just to put that on our reaction map, this is what going to kind of look like. We've got, starting with, often you'll be asked to do something based on an alkane or alkene starting reactant. So for example, if you needed to make a haloalkane from an alkane, then you could say, well, I'm going to have let's do it for methane. Got methane, and then we're going to react it with chlorine and ultraviolet light. You can write the chlorine in the line like a kind of normal one, or you can write it above the line if you like, just because often when we're writing the organic ones here, we're only putting the organic compounds before and after, because we're not super interested in exactly what the other product is. So if we're putting the chlorine in the line, chlorine, then we're going to end up with HCl coming out the other side. If they do say a balanced equation, then make sure to write it like this. So we do get out hydrochloric acid at the end. That's just kind of a waste product. We don't really use it for anything else. All right. So from here, we can do a lot more things with a haloalkane than we can with just the alkane. So often we're reacting with the chlorine, not because we want that chloroalkane, but because that chloroalkane is easy to turn into something else. So it's easy to do another substitution reaction with that. It's easier to substitute something with a chlorine because the chlorine is more stable by itself than it is to substitute it with a hydrogen, because a hydrogen isn't stable by itself. So it also helps that when we have a compound, in this case here we've got our chloroalkane or chloromethane here. The chlorine is more electronegative, so it'll pull to this side, make it more electronegative, and make the carbon a little bit positive, which means that if something else that's negative comes along, it'll be attracted to this carbon in the middle, and it can come along, react here, and kick off this chlorine. Now, if we compare that to trying to do the same thing with just methane, well, there's no delta positive here. There's nothing that's just a little bit positive, so the OH doesn't really want to have anything to do with any of this, and it'll just kind of hang out. If anything, the carbon would be a tiny bit positive, a very small amount. So by having the electronegative element here, the electronegative chlorine on here, then the hydroxide ion can come in here, attack this carbon, and the chlorine will leave as a chloride ion. So you can do lots of reactions with this. You can basically take anything that's negative and try and shove it in here. The two main ones that you need to know for this here are that if we had a hydroxide like this, we'll end up making an alcohol. So if you imagine the chlorine leaves, the OH stays on, you end up with this, so it's an alcohol. Or you can do the same thing with NH2 and you'll get an amine. So OH is going to produce an alcohol, NH2 or NH3 in this case is going to produce an amine. So just to talk about those briefly, normally the way we provide this OH is through sodium hydroxide. You could do it with another hydroxide. Sodium hydroxide is kind of just the one that we'll say for the sake of it. So we take a haloalkane, we add sodium hydroxide, the hydroxide will come kick off the chloride, and it'll produce sodium chloride. Now, we're not bothered. Yes, technically, if we did ionic equations, we could remove the sodium because it wouldn't really be reacting here, assuming we're in a polar solvent. But for the sake of this, you can just leave it like this. And the other way we can get this to work is that you can do this with water as well. Sodium hydroxide is kind of the easier one just because it's stronger. Like it makes sense that the oxygen here is more negative because it has a full negative charge, whereas if it's just water, it's only a little bit negative. So we want this full negative charge and the reaction should go a bit smoother, but technically you can do it with water as well. So one thing to note here is that we'll get different types of alcohol based on where the reaction is. So if you imagine that you've got propane, if you've got the chlorine on the middle carbon here, so we've got 2-chloropropane versus if we had 1-chloropropane. the 2-chloropropane, we replace that. We're going to end up with a secondary alcohol. So the OH is on a carbon connected to other carbons. Whereas if we've got a 1-chloropropane, so the chlorine's on the end, we're going to end up with a primary alcohol. And this is going to matter for a bit of the next reaction we talked about, where we're going to get slightly different products depending on whether we have a primary or secondary alcohol. Slightly different. We're going to get different products. So here's our kind of overall one there. So you can take a haloalkane, add sodium hydroxide to it, and we'll end up with methanol. So we can add that on here now. So now we know how to go from an alkane all the way to an alcohol. So note that this bit in the middle, it's an intermediate. We do form it, it does exist, but we normally just take it out and then go and react it to form something new. We're not necessarily trying to make this, and you'll see that when we put more arrows on, we can end up with products down here, and we can make our way through different reactions to get from one side to the other. You can't jump straight from the alkane to the alcohol. We need to go via this intermediate. Amines is pretty similar. Instead of hydroxide here, we're going to use ammonia. So ammonia is going to, so we're going to have chloromethane. Ammonia is going to come in. We know ammonia, the nitrogen is a bit negative. It's going to come in, attack the, call it nucleophilic, so the positive carbon. Oops. And then the chlorine is going to leave as chloride. So we could write this out here in full as well if we want to, and we'll end up with hydrogen chloride coming off again. So we can put that on here as well. So we take our halide alkane, we add ammonia, and we'll get an amine. So we talked about alkene reactions as well. So we've got our double bond in an alkene. The alkene, that double bond is normally weaker than the single bond. So it's more reactive, and we can lead to lots of different reactions. Most of these being addition reactions. So we add some kind of compound, like chlorine here, and basically it's going to take the molecule, it's going to split in half. One of it's going to add on to one side, one of it's going to add on to the other side. So there's a few that you need to be aware of. You need to know that if we take an alkene and we add hydrogen with nickel or platinum present, you'll get an alkane. If we take an alkene and we add halogenated acid, so like HCl or HI or HF or whatever, we'll replace, we'll form two different isomers of the haloalkane. So if we've got this one, for example, and we've got hydrochloric acid, we can either have the chlorine go this side or that side. If it goes to the middle, then we'll end up with this one here. So we can end up with that, or we can end up with, if it goes to the other side, it'll end up here. And you'll notice that this will give us the 2-chloro and the 1-chloro that we talked about before. And then depending on this, we'd end up with the primary or a secondary alcohol. So you can separate these out once you've made them, but you will always end up with both isomers being produced here, unless you're doing something tricky and adding on extra groups to stop one of them from forming or something like that. So that's the second one. If we just add the halogen, then there's only one possible thing that comes out. So if we just add chlorine here, the only possible result would be to have a chlorine on each carbon. And if we add water, then we can actually make an alcohol straight from an alkene. So we have the OH here. We can imagine that we've got the H adding to one bit, and we've got the OH adding to the other one. And we can see that we could get potentially get different isomers here as well. For this one, the reagents that we need are acid, so phosphoric acid is the one that's normally used, and we'd use some heat here. Sometimes you might see the heat written as just a delta. You might see the heat just written as a delta over the arrow there. So let's add those onto here. So we've got our new one here. We can go from an alkene to an alkane. It's not super common. You do need to know it, but it's not normally a particularly useful reaction just because the alkene is more reactive in the first place, and we can already turn it into lots of things. So we can already turn it into the alcohol here. So there's no point. So theoretically, yes, you could take the alkene, turn it into an alkane, turn it into a haloalkane, turn it into an alcohol, but that's kind of a waste of time. You could just do it in one step with adding water here. So water, phosphoric acid, and 300 degrees. We can also turn it straight into the haloalkane. So even if you wanted a haloalkane, there's no point going to it through the alkane. We can go straight there. We can also have the dihaloalkane as well. All right, so we're about halfway through our reactions. So with this, you should be able to answer the 11.3 review questions. So you can go pause the video, have a go at those ones. It's only a few questions, but it should help you consolidate on those reactions. Now we'll keep going. So next up, we have alcohol oxidation. So we can oxidize alcohols with different things. One thing to be aware of is when you hear oxidation and reduction for organic chemistry, they'd mean the same thing as when we talk about redox with metals and things like that. But a nice shortcut is that when you hear oxidation, it normally means to add oxygens, and reduction is to add hydrogens. So when we took a double bond before and we added hydrogens across it with the help of the nickel or platinum catalyst, that was a reduction reaction because we increased the number of hydrogens there. So that's another little shortcut there. So if we're saying we're oxidizing an alcohol, we're saying we're adding more oxygen to it. Or the other way you can look at it is to reduce the amount of hydrogens that are on it as well. So for this, the main reactant is dichromate. So it's Cr2O7 2-. So again, useful one that you do need to know. And it is catalyzed by some form of acid. Normally we use sulfuric acid. Now, there's a couple of different options for what will happen here, depending on what type of alcohol we have. If we have a primary alcohol, it will go through a process. It'll go first to an aldehyde, and if we leave it in there with all the reactants and keep heating up, it'll turn into a carboxylic acid eventually. So if we start reacting a primary alcohol and then we stop the reaction after a few hours, then we'll end up with an aldehyde. If we just leave it there for a few days, then we'll end up with a carboxylic acid. So you do have options there in that reaction. On our pathways, I will just draw the alcohol to a carboxylic acid thing in terms of the room that we've got on the slide. If you want to add on the aldehyde into there, you can do that as well. A secondary alcohol is oxidized to a ketone, but it doesn't go any further. If you keep it reacting, it'll just stay as a ketone. It can't turn into a carboxylic acid because it's not at the end of the chain. It's in that middle. And if you've got a tertiary alcohol, then it just can't react at all. It won't be oxidized. So to put that in, to write them out here in terms of the structures, we've got butanol. We react it here. Remember, we've got Cr2O7 2- and some kind of acid source. We've got butanol. This is butanol. Remember, you don't need to know how to name these ones. And we've got butanoic acid here. I should say butan-1-ol here. We can take butan-2-ol. So it doesn't matter where the OH is because it's going to change to what reaction is going to happen here. So remember, we said that structural isomers have different reactions even if optical isomers don't. Again, we put some dichromate in there with some acid. And we'll end up with butanone. Should be butan-2-one there. Again, you don't need to know how to name ketones. And when we have 2-methyl propane 2-ol, then that actually just can't react at all. Just won't form anything. So because we've got a primary one here, I've only drawn the final reaction, taking it to a carboxylic acid, because we can react carboxylic acids. We're not talking about reactions of aldehydes this year, so I haven't put it on here. but you could theoretically stick it in the middle here if you wanted to have everything on the one thing. It's the same thing there. All right, let's keep going. So next up we have reactions of carboxylic acids. So we can react carboxylic acids with either alcohols or amines. So first one up here is if we react a carboxylic acid with an alcohol, which we've already talked about, we have what's called an esterification reaction. You do need to know the name of that. Sometimes it pops up as like a short answer or something like that. In the presence of acid, which catalyzes the reaction, the carboxylic acid plus the alcohol is going to turn into an ester, and it releases water. If it releases water or some other small molecule, then we call it a condensation reaction. So you need to, again, we need to have an acid. Again, normally just use sulfuric acid for this one. So this is a condensation reaction. We'll talk a lot more about them when we get into food chemistry. These two few reactions here with carboxylic acids are super important when we get into food chemistry and just biochemistry in general. So we've got esterification going this way, esterification being a condensation reaction. We can also take an ester and turn it into a carboxylic acid and an alcohol, again, by doing the opposite. So if we add water, then we'll remake the carboxylic acid and the alcohol. It also means that if you get an ester from something, so you can get esters from food and stuff like that, you can take that ester, break it down into the carboxylic acid and alcohol and use them for different things. So we call this a hydrolysis reaction. Again, hydro meaning water, and lysis meaning to cut. So we're cutting a molecule in half using water. So add that here. We've got our alcohol and our carboxylic acid. They combine together to make our ester here. So often when you're asked the question in the exam, an ester ends up being your final product that you need to make. And we could also make these reversible. If for some reason you had an ester as a starting product and you need to make an alcohol, it doesn't normally happen like that. Normally esters are harder to get, so normally we're making them rather than trying to turn them into other stuff. The other reaction we can do with the carboxylic acid is we can add an amine to it, in which case we'll get an amide being formed. So here I've added a primary amine. This could theoretically work if you just added ammonia as well. So if I have that there, can add ammonia and get something similar. So we get an amide out from this. And again, it's reversible. We can take our amide, split it up, and turn it back into the amine and the carboxylic acid. So we add that on there, bit of a crossover here, but you can see amide is often the other final product. So often we're starting off in like the alkanes, we go, okay, we're going to need to go here, then go here to make that. So you should be able to answer the 11.4 questions now. And theoretically, using some logic, you should be able to answer 11.5 questions as well. I'm just going to run through them here, through the kind of logic quickly here with some practice questions though. So go and finish 11.4 and then you can come back. So the next bit here, you need to know how reaction pathways work, which is basically just doing one reaction and then doing another reaction, then doing another reaction until you get to your final product. So we're going to string together multiple of those individual reactions. We're kind of going to make basically something reacts, it forms something else, reacts to form something else, and then that's going to form the product at the end that we actually want. So got an example here. How can we make propan-1-amine out of propene? So start off there. Let me just draw that out. I'll use skeletal because I'm lazy. So we've got propan-1-amine. How are we going to get from here all the way to here? Well, let's have a look. So we're going to start with we're starting with an alkene, and we need to get to an amine. You don't normally get given compounds with multiple functional groups for these reactions. So if we want to go from there, okay, so we're going to need to go, we could theoretically turn it into an alkane, turn it into a haloalkane, and then turn it into an amine. We normally want to reduce synthetic steps as much as possible, just to make sure, just because our yield isn't 100%, we'll lose more product over time, which we'll talk about in a second. So that's 3 steps. Instead, we can do 2 steps. Go 1 and go 2. So first up, we want to take our alkane and add hydrochloric acid to it. Let's add hydrochloric acid. Now, remember that the hydrochloric acid would make 2 isomers. The only one that's going to work, notice that our amine is going to end on the first carbon, so that's where the chlorine is going to have to end up. So we're going to end up with this. Oops. And then we've got to here. So to get to here, we're going to need to add ammonia. Let's add ammonia, and then we've got our product. So that's our kind of reaction pathway there. Hopefully see how that works. Let's keep going. You can see that there is a little bit of common sense here in terms of we had to say, well, the chlorine is going to end up here. If this reaction theoretically could make this one as well. So in real life, there would be a separation process where you'd have to take out the correct isomer and then react it. Otherwise, you'd end up also getting this compound out as well at the end. All right, do another one. How can we make methyl butanoate from butanol and methane? Okay, so when we've got esters and amide, we have to start thinking about 2 reactants to get to our final product. Technically, you can start from 1 reactant and turn them into both the alcohol and the carboxylic acid if you had something like ethyl ethanoate or propyl propanoate or butyl butanoate if they had the same amount of carbons. But most of the time, you'll end up with 2 different amounts of carbons. So we've got butanoate, so 1, 2, 3, 4. And remember that the carbonyl is on this side. So this is the C double bond O side. The other one is the O something side. So O, and then we've got methyl here, like that. So when we go back, we can use what's called a retrosynthetic arrow. And we basically just write it as, well, what's it gonna have come from? So it's gonna have come from, oops, messed that up, 1, 2, 3, 4, butanoate. It's going to come from 1, 2, 3, 4. It's going to come from a carboxylic acid, and it's going to come from an alcohol. So let's draw our carboxylic acid out first. So we're going to need butanoic acid, and we're going to need, what's on the other side? We've got methanol. All right. So we can do these one at a time. So we've got butanoic acid. So we're going to have 2 different pathways. I'll do one in red and one in blue. So we've got butanoic acid, and we need to get there from butanol. So we're going to need to go from here to here. So that's one pathway we're going to need to do. And the other pathway, I'll do that. All right. And for the other one, we're going to need to go from methane to methanol. So we're going to need to go from the alkane, and we're trying to get to here. So we're going to need to go here and then here. All right. So let's think about the carboxylic acid first. So we've got butanoic acid. We would have to make it from the alcohol of that, which is going to be butanol or butanol. Oops. So 1, 2, 3, 4, the OH, and we're going to have reacted it with H+, so I'll say sulfuric acid and dichromate. H2SO4, dichromate here. And I used the wrong color for that. All right, so for our other one, we've got methane, we're going to methanol. So let's look back one step. Okay, we're going to need to have gone from chloromethane. and we're going to need to have added sodium hydroxide. And from that, we're going to have gone from methane to get to the chloromethane. And we're going to need to have added chlorine and UV light. Now, technically, you don't have to use chlorine here. You could just use something else. Chlorine's normally a pretty good middle ground. So there's our kind of reactions there. So often the way you'll see it written in an exam is they'll go yada, 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 and then there'll be a box and they'll say, I swear there's one of these every year. They'll say, and then one of the questions will say, oh, what reagent goes in box J? And then what compound is made in box K or something like that. So often that they've got the pathway written out for you already. I'm doing this from scratch, so it's probably a little bit harder than how Vika always says it as well. But if you can do this, then you'll be able to do anything that Vika throws at you. All right, let's do one more. Describe a synthetic pathway to produce the molecule below from alkane and or alkene starting materials. So here's a pretty hard one. We've got, hopefully you can identify what molecule we have. We have an amide group here. So when we, and we're going to make that from, we're going to make our amide from an amine and a carboxylic acid. And we can kind of think about which ones they are from splitting it up here. So this side is going to be the carboxylic acid side. And this side is going to be the amine side. So I'm going to put them both on this slide. So I've got some more room. There we go, and we can think about those. So on the one side, we've got this carboxylic acid here. Not going to bother naming it. Jokes is 3-metal butanoic acid. So we're making it, and it says here from alkane and or alkene starting materials. So we just need to basically find the shortest path we can go from an alkane or an alkene. So I've got a carboxylic acid. What's the shortest way I can go back? Well, I can form it from an alcohol. I can form the alcohol from an alkene. So let's think about it in 2 steps. So what would this be as an alcohol? Well, the bit off the side would be the same. But instead of this being the carboxylic acid, it's going to just be an alcohol there. Now to go from the alcohol to the carboxylic acid, we would need to use dichromate, and we would need to use some acid. So I'll put those on there. And then I should probably put this in here as well. Put the final product in. That is actually an important part of the reaction. 1, 2, 3. All right, and the alcohol came from an alkene. So an alkene with OH on the side. Like that. And the alkene was made by the alcohol is made by a phosphoric acid at 300 degrees. Just add delta to show that there's heat there. On the other side, we've got propanamine. Propanamine we can make from, we can go back, well, we can either make it from an alkane or an alkene. Normally, an alkene is just preferable from a realistic standpoint, so I'm just going to go with that. You could do the same thing with an alkane if you liked. So amine has come from a chloroalkane. So we're just going to say, have something similar with chlorine there, 1, 2, 3, and it's going to react with ammonia. All right. And before that, it was an alkane. So instead of the chlorine being there, there's going to be a double bond there. Like that. And we're going to have added hydrochloric acid across that double bond there. All right, so we've got two alkenes here, sorry, and we've got a way for them to both react to form this funky final product here. All right, so you should be able to answer the 11.5 questions now, so you can go and do those, and then we'll finish off the chapter. So the last bit here isn't really to do with reactions at all, but to do with ways that we can mathematically describe basically kind of how good a reaction is. So most of the time, a reaction isn't 100% efficient. Not all of the reactants have turned into the products that you want. So some of this is because you've got an equilibrium and some of the products have just turned back into reactants. Sometimes it's just that not all of the reactants have reacted in the time you've given it. And sometimes you've got side reactions. Well, a lot of the time you have side reactions. So the things that you've put together in the beaker or your conical flask or whatever have reacted to make something different that you didn't want. So we already talked about side reactions a little bit in terms of batteries as being one of the basically the reason why the capacity of a battery decreases over time. So we end up with two values from this. So we have a theoretical yield. So we'll talk about this in a second. We've got a theoretical yield and experimental yield, and they don't normally match up. If something's 100% efficient, then they match up, but other than that, they are not the same value. And we basically get this equation here, which is given to you in the data book, which is nice. The percentage yield of something is going to be equal to the experimental yield over the theoretical yield times 100%. So experimental yield is literally just take your product once you're done making it and weigh it. Note that you are working under the assumption that your product is completely pure. So if we do this in the lab, it's quite possible that the value that you're getting isn't 100% accurate just because of a variety of reasons. Either some other product has been made, or it might be that there's just water or something in your sample. A lot of the time doing syntheses at uni, you end up with a 300% yield value, which doesn't make any sense because 100% is the maximum you can get out. But you end up with 300% value because your final product just has tons of water in it. So experimental yield is literally just you have your product, you stick it on a watch glass, you put it on a scale, and you get that value out. There's no way you can calculate what value this will be without just doing the synthesis and then finding it out for yourself. So if this is we're talking an exam situation here, you always have to be given this. The theoretical yield is basically just using stoichiometry to say, well, if I added 3 grams of a carboxylic acid and 3 grams of alcohol together, what mass would I expect to come out the other side? So this is just coming straight from, you should be able to take those values, use stoichiometry, calculate what the expected mass of your ester is, in this case here, and then compare that to what you've actually found. So, for example, we've got 15.2 grams of ethanoic acid at excess butanol. So you're not expected to do limiting reagent questions for this. You're only expected to be able to do excess reactant questions. So produce a 22.5 grams of butyl ethanoate. What is the percentage yield of this reaction? So straight up, we've got 22.5 is our experimental yield here. We're going to need to find out the theoretical yield. So we've got, remember, ethanoic acid is CH3COOH. So I can simplify that down, go to C2H4O2. And C2H4O2 plus C4H9OH is going to make butyl ethanoate. Let's just draw that out really quickly. 1, 2, 3, 4. So we've got 6 carbons. Now I could, just for counting purposes, 6 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? Like that. And we're going to end up with some water there. So again, just like all stoichiometry, you can do this in different ways. I'm just going to do it the kind of diagrammatic way here. We've got 15.2 grams. We're going to divide it by the molar mass. The molar mass is going to be 24 from the carbons plus 4 from the hydrogens plus 32 from the oxygens, so 60. Oops. 60, so we've got 15.2 divided by 60. We've got 0.253 mole to start off with. Now we'd expect the ester and the carboxylic acid are both just 1 in the reaction. So we would expect 0.253 mole of the ester out the other side. And then we're going to multiply it by the mass of the ester, which is going to be 6 times 12. So 72 plus 12 from the hydrogens plus 32 from the oxygens. So 116. So we go 116 times 0.253, 353, and we would expect 29.387 grams out the other side. We can see it, these values don't match. So remember our yield equation. Yield is going to be equal to the experimental yield, 22.5, over the theoretical yield, which is this value. So 29.387 times 100. So 22.5 divided by our previous answer times 100 is going to give us a, what are we going to round it to? 3 significant figures, 76.6% yield, which is pretty good. Not too bad. All right. We can also talk about the yield for a whole pathway. So if you know the yield of each step, so if we've got a synthesis, for example, that has 3 steps, so the chlorination of the alkane, so the substitution reaction has a yield of 90% somehow, and then the reaction to the substitution reaction to turn the chloroalkane into an alcohol has a 50% yield, and then the oxidation to a carboxylic acid has a 10% yield, for example. If we wanted the overall yield, we just need to multiply all of them together. Which kind of makes sense, right? Like 90% yield effectively just means you've lost 10% of it somewhere. So you've got 0.9 of your product remaining. So we can just take all of these and multiply them together. So 0.9, which is 90%, times 0.5 times 0.1, multiply them all together, times it by 100 is 4.5%. So that is going to work there. And the other way we can do it is if you know the starting mass and you know the final mass, you could take the theoretical yield through the whole thing. You can find out what mass you're expecting from the final product, and then just take the experimental value, divide it by the theoretical times 100, and do exactly the same thing there. So obviously it's nicer because that one would require you to do stoichiometry twice or 3 times if there were 3 steps. Obviously nicer if you get given a percentage. Otherwise you're basically just doing the same thing multiple times in a row. All right, so last thing here. So talking about yield is basically just how well does your reaction work? What percentage of your reactants are actually turning into your products? So yield is a very experimental value. It's a very much a thing, an empirical value. So you have to just do the experiment and then you look at the yield and then you find it out. You can't really do maths without having done the experiment. So any question that you'd see there, you have to be told, oh, and Joe did the reaction and got 30 grams of product out. Someone has to have done the reaction. In comparison, atom economy is, again, we're talking about basically how much loss we have in a reaction, with a higher percentage being better. Atom economy is more of a theoretical value though, or it is a theoretical value. So it's mostly when we're talking about environmental and economic viability of a reaction. Is this reaction good for the environment? i.e., are we not just making massive waste products in our reactions? And is it good economically? If we're spending 100 grams of reactants to make 1 gram of product, we're losing 99% of the stuff that we actually spent money on. So we'd prefer to keep that value as high as possible. So atom economy is basically a measure of out of the atoms that are in the reactant, or we're going to use mass values, out of the mass of stuff that you put into a reactant, what mass do you get out? 100%, we would expect if we put 50 grams of stuff in, we get 50 grams of stuff out. Obviously, it's impossible to get higher than 100% because you can't put 50 grams in and get 60 grams out because that's not how law of conservation of mass works. So 2 ways we can do that. You can see they're basically the same thing. We can look at the molar masses of the reactants and the products, or we can look at the mass of the reactants and the products. Each one, I should times these by 100 as well, the percentage. Each one of these is we're basically just looking to look at the ratio of useful stuff to that we get from the product to the overall amount of reactants we put in. So either the molar mass of the useful products divided by the molar mass of the reactants, or the mass of the useful products over the mass of the reactants. So just as some examples here, we've got the Claisen rearrangement here. Because this is a rearrangement, we end up with the molar mass of the final product being equal to the molar mass of the reactants because none of the atoms disappeared. Literally, it's just this double bond here reacts over here, and they kind of react like that, go around in a circle. Because of that, because there's no atoms lost, we end up with 100% atom economy. In comparison, we've got a reaction here where a base comes in, it's going to pull off this hydrogen, and that's going to make a double bond here and knock off a tertiary amine here. So in comparison here, if we're only talking about useful stuff here, so for this one here, we're saying that if we want this reactant in particular, this reaction, we would take the mass of the molar mass of this thing. So it's 36 from the carbons, 37, 38, 39, 40, 41, 42. So it's got a molar mass of 42. And the molar mass of the reactants, once you add it all up, is 119. The atom economy is going to be this molar mass divided by the molar mass of everything on this side. And we find that it has an atom economy of 35%. So what it just means is that 65% of the mass that you're putting in there is just being ejected as other stuff that you don't want, which is kind of a waste. Now, higher atom economy is always better. Of course, you can't really compare any two reactions in terms of atom economy. You can't just say, well, the Claisen rearrangement is clearly better than this top reaction here just because it has a higher atom economy. Yes, that's a good thing, but you can't make every product using the Claisen rearrangement. So we'd have to compare this to some other reaction that would also produce the same propane. So let's have a think about this. So what's the atom economy of a single substitution reaction between butane and chlorine? So we can put them in here. Note that you don't really need the structural formulae for this one, as long as you know the molar mass. That's fine. So we've got a single substitution. We swap one hydrogen with a chlorine, and the useful product is the haloalkane here. If there's some ambiguity, then it should be clear in the question which one's the useful product. Otherwise, it's probably just the organic one. So you wouldn't do a substitution reaction to make hydrochloric acid. That's pointless. So in this case here, we'll look at our molar mass of the haloalkane here. So this is going to be 48 from the carbons, plus 9 from the hydrogens, plus 35.5 from the chlorine, so we're at 92.5. So it's going to go on the top of our fraction. And on the other side, we've got our butane is going to be 58, and our chlorine is going to end up being 71. So we'll end up with 71 plus 58 over here. Put that all together, 92.5 divided by 71 plus 58, multiplied by 100, and we get 71.7% atom economy. Again, not terrible. We do lose a fair bit out from the hydrochloric acid here, especially because the chloride is quite heavy. You can imagine that if we swap this out for a fluorine, we would actually make it more efficient because we're losing. We would increase the atom economy because the fluorine is lighter. All right, let's do another one. What is the atom economy of the hydrolysis of propanamide to produce propanoic acid? All right, so propanamide is going to be 1, 2, 3. Amide here, and we're hydrolyzing it, so we're going to need water, and we're going to get propanoic acid out of it. Now you don't really need to write down what the other stuff is. In this case, it would just be ammonia, but we only need to know the useful product. So this one here, we've got 1, 2, 3 carbons, so we've got 36. 2 oxygens is 32. We're going to have 1, 2, 3, 4, 5, 6 hydrogens. So it's going to weigh 74 overall. Let's put that as our numerator. Over here, we've got water's 18 plus 36 plus 16 from the oxygen, 14 from the nitrogen, and 1, 2, 3, 4, 5, 6, 7 for the hydrogens. It's going to be 73. Times that by 100. 74 over 18 plus 73 times 100, and we're going to end up with 81.3% atom economy over here. All right, so you should be able to do the practice questions in chapter 11.6 now. But before you go and do that, just to recap our learning intentions here. So you should be able to have a look at the statement here and say, well, I know all of the reactions here. Or you don't necessarily need to know that now, but you do need to know that by the time the SAC and the end of the year exam roll around. You need to know those reagents, and you need to be able to write equations for them and be able to put them in terms of a pathway. So there's a bit of remembering to go in there. Again, I highly recommend putting that into a flowchart and using that there. You should be able to calculate the atom economy and percentage yield for a given reaction. All right, so that's basically it for organic chemistry in terms of the reactions and the molecules themselves. What we're going to be looking at from now on is the kind of analytical side of that, looking at chromatography, some different spectroscopies for identification, and some volumetric analysis to look at what concentrations of samples we have. So hopefully you've enjoyed this organic section of the course. Let me know if you've got any questions, and I'll see you when I get back.